Ending this week's edition of the Center for Imaging Sciences weekly seminar series. And in case you don't know me, I'm John Karakis, a research faculty here at the center, and I have the pleasure of introducing our guest speaker today. He's Eric Choi from GHGSat up in Canada. Eric is currently the Director of Business Development at GHG, but he has a technical background, including technical and managerial responsibilities for aviation and space sectors. He's also worked on a number of satellite platforms, and he has a BA in engineering science and an MA in aerospace engineering from the University of Toronto, as well as an MBA from York University. And he's an alumnus of the International Space University. He is also, fun fact, an award-winning science fiction writer. So perhaps we can ask him some questions about that as the seminar goes on. With that, I'm going to put the microphone next to the speaker here and the laptop. And Eric, why don't you go ahead and say a few words? We'll see how well that works.
Well, John, thank you for that great introduction. And maybe as a way of testing the hardware as well, how do I sound right now?
Eric, are you talking? We don't hear
I
anything.
was. How do I sound?
Very
Are
good.
people on Zoom able to hear me?
Yes, on Zoom, you're loud and clear.
Yeah, so it looks like I'm loud and clear on Zoom, and there seems to be a
We had it
last
coming
line
out of the
problem
laptop, but
here.
now it's stopped. Eric, go ahead and try again.
All right. How do I sound now?
We got it. How does it?
All right. It's great. Well, John, thank you for that wonderful introduction, and thank you for the opportunity to do this. I recall that this actually goes back a while. I think we met in person at the JC workshop about a year ago, almost exactly at USGS, and you very generously mentioned this seminar and so kindly invited me to participate. I regret that I'm not there in person, but I hope that there'll be future opportunities for all of us to get together face to face and chat more about instrumentation and all kinds of interesting stuff. So maybe for the next 45 minutes or so, I would like to leave some time for questions. I'd like to talk about a topic that perhaps in the current environment might actually be considered controversial, but the role that satellites, and particularly satellite imaging technology, has in both climate change mitigation and emergency management. And it's in the context of what my employer, GHGSat, has been doing for the last number of years with its satellite technology. So as the name implies, greenhouse gases, evokes really two species come to mind, carbon dioxide, of course, but perhaps the sort of the lesser known brother to carbon dioxide, which is methane. And so our satellites are actually tuned. The majority of our operational constellation is tuned for the remote sensing of methane rather than carbon dioxide, although we do have one carbon dioxide satellite at this point. And the reason for that, this dates back to the founding of the company back in 2011, was the recognition that in some ways methane was, as I said earlier, kind of the neglected sibling of the much more famous and perhaps better looking carbon dioxide. But the fact of the matter is that this is a very potent greenhouse gas. It's about 83 times the global warming potential of carbon dioxide over the first 20 years in its release into the atmosphere. And indeed, a quarter of today's global temperature increases have been attributed to these anthropogenic methane emissions. So, that's sort of the bad news. But the good news is that if there were ways to identify methane emissions and to shut them down. There would be a commensurate and proportional benefit in terms of climate and public health. And I'll say as well is that methane, while it in itself is a non-toxic species, although obviously it is an asphyxiant, it's typically co-emitted with various VOCs, various volatile organic compounds, and these are things that are precursors to phenomena such as smog and ground level ozone. So when all of these things are put together, it makes a very compelling case to identify, quantify, and mitigate methane emissions wherever they may be across the globe. And it really is a global emissions problem. And so it sort of becomes very logical that sort of the high frontier or sort of the upstairs of space, if you will, is an ideal domain for looking down at the Earth and quantifying and mapping out these particular species. This diagram, I should probably credit this in the future. This is from Danielle Jacob of Harvard. And I guess if poor Danielle could get like $10 for every time someone like me used this diagram, he'd never have to apply for grants again. But he's got this beautiful diagram that I'm sort of pilfering here that illustrates sort of the two classes of methane instruments or methane equipped sensing spacecraft. And they're broadly divided into sort of wide area flux mappers versus the point source imagers. So the first of the greenhouse gas satellite missions that were launched, it was an instrument called SCIAMACHY. It's some kind of acronym, and don't ask me what that acronym stands for, but this was an instrument that operated on the European Space Agency's GHGSat satellite that was launched in 2022 and operated for about a decade until 2012. So that particular instrument was not particularly tuned to greenhouse gas relevant bands, but the first satellites that were dedicated to specifically greenhouse gas measurements were the JAXA Japanese GOSAT spacecraft that was launched in 2009, and the NASA OCO2, the Orbiting Carbon Observatory, that was launched in 2014. There was actually an OCO1, but it was lost due to a launch vehicle mishap. And these particular spacecraft were followed up later, most notably by a fairly significant instrument in this field called TROPOMI. This is the tropospheric monitoring instrument that is currently operating aboard the European Space Agency Sentinel-5P spacecraft. And this has been in operation since 2017. And I'll talk a little bit later in the presentation about the relationship between these area flux mappers like TROPOMI and the point source imagers like GHGSat, which is what we do. So for something like TROPOMI, these area flux mappers, they typically have very wide fields of view. So they have a swath, I believe, in the case of TROPOMI, something on the order of about 2,500 kilometers, but they have commensurately coarse pixels. So in the case of TROPOMI, I believe they're about 5 by 7 kilometer pixels. And in terms of their methane sensitivity, these are tuned towards the larger fluxes, so on the order of several tons per hour of CH4. Whereas in the case of GHGSat, what we've done is we've taken the opposite but complementary approach. As a point source imager, we have a relatively small field of view, about 12 by 12 kilometers, but commensurately high spatial resolution. So spatial resolution on the order of 25 meters, and also a much lower detection threshold than these area flux mappers. So our detection threshold is 100 kilograms of methane an hour. So we have presently a constellation of these spacecraft on orbit. I apologize, this chart is actually a little bit out of date. The 12th satellite corresponds to a technology demonstration satellite that we launched in 2016 that is no longer providing operational service, but we have 11 commercial operational satellites, 10 of which are dedicated to methane monitoring, and the 11th satellite is tuned actually to a carbon dioxide band. These are all in a polar sun-synchronous orbit, basically going from the North Pole to the geographic South Pole. And as the Earth rotates underneath it, we have basically worldwide coverage of every spot on the Earth, both land and water, and basically in almost in all seasons as well. Just as perhaps a bit of an aside, you might notice some of the names here. We've actually named all of our satellites. And if you're wondering where this comes from, these are actually the names of the kids of the members of the team. So this is just sort of a little thing we do to, it's a bit special. It just reminds us of the mission of what we're trying to achieve, with the hope for a better future for the generations to come. And maybe just to give you an idea of what one of our satellites look like. So this is three of my colleagues dressed in their best clean room attire, all masked and gowned up and hair netted. And so this is one of our flight spacecraft right there. It's not very big. It's probably about the size of a microwave oven, mass about 30 kilograms. So this is very much in the microsatellite class that you've probably heard about. This isn't, these ginormous sort of James Webb Space Telescope or Hubble Space Telescope or space station type of spacecraft that you've probably seen on TV in the movies. And it's really been this new space, microspace revolution over the last couple of years that has enabled a small and medium enterprise like ourselves. We have 160 employees to be able to accomplish something that up until now has actually not been done by the large space agencies. That is, having a large multi-satellite constellation specifically for point source imagery of greenhouse gas emissions. So what do one of these observations look like? It looks something like this. So as I said, the spatial resolution on the ground is on the order of 25 meters. And the benefit of that, as you can see here, is it enables us to attribute a methane plume right down to a source, be it in this case, an oil and gas platform, probably somewhere in a place like the Permian Basin. And this is very valuable to the energy sector, to the oil and gas sector, to the waste management sector. I'll say that the vast majority of our users and our customers are actually in that industrial space. And they're doing this for very sound business reasons, because when you have a gas leak like this, it's basically money going out into the atmosphere. Whereas if you were to be able to responsively find these leaks, plug them, recapture and resell that product, that's basically money in the bank for the particular operator. So as I said, we have a detection threshold of 100 kilograms per hour. And another key metric for our constellation is the revisit rate. So for each individual satellite, basically as a measure of when that satellite, the nadir point of that satellite is pointing at exactly the same point in the Earth, for each individual satellite, it's on the order of 14 days. That roughly scales linearly to the number of spacecraft we up there. So with 11 spacecraft now, that basically at the constellation level means that we can revisit any given site, not every site, but any given site on the planet approximately every 1 to 2 days. And we recently brought on the capability of being able to deliver an observation to a user within 24 hours of its observation by the satellite. The instrument that we use is a passive instrument. It operates in the shortwave infrared, and I'll provide a little bit more detail about that in subsequent slides. I was actually hoping that Lee Murray from the university, your neighbors at the University of Rochester, might have been able to join this seminar this afternoon. But as a way of illustrating another example of the work and the observations and what our imagery actually looks like, we did a campaign under Lee's leadership where over the course of a year, we were looking at methane emissions from 5 landfills across the state of New York. And again, this was done at a roughly monthly cadence of observation over the course of a calendar year. And this was to help quantify things like seasonal variations of this phenomenon over the course of a year. Lee's working on a paper on this. This is going to be shortly documented in the scientific literature, and ultimately the expectation is that this could potentially lead to informing potential statutory requirements for these types of emissions in the state of New York. So this being an instrumentation group, I thought I'd delve into a little bit of detail about the instrument technology itself and how it works. And really, it's very straightforward. It's in many ways, it's sort of remote sensing 101, if you will. So as I said earlier, we're a passive instrument operating in the shortwave infrared. We look at a fairly narrow band between about 1630 to 1675 nanometers. And very simply, we have photons from the sun coming down to the planet, reflects off the surface, comes back through the atmosphere and into the input aperture of our instrument. And from the various, either absorption or scattering spectra in that band, we infer the concentration of methane over the particular field of view. So if you were to look inside that microwave oven-sized spacecraft of ours, you will see that the vast majority of it is taken up by the optics. So, you peel it open in this sort of schematic, this ray trace diagram here. So light would be incident from the left, and there are 3 lens assemblies labeled L1, L2, and L3 here. So L1 and L2 is essentially a telescope. It collimates it down to a bandpass filter that gets us, so it's passing to the 1630, the 1675, to the spectrometer, and then there's a third lens assembly, which is essentially the it's basically the imaging lens that focuses down to the detector assembly. So if it was only this, basically we'd have a very nice visible light camera there operating in low Earth orbit. But we do have, of course, a few additional optical elements to spectrally discriminate the incoming light that's been collected. So obviously that incoming light bears with it some kind of spectra. There'll be the dips in depending on the absorption of various species in the atmosphere, which you can see sort of on the chart on the bottom left there. So these are absorption features from species such as methane, carbon dioxide, and water vapor. So the spectrometer we have is based on a Fabry-Perot interferometer. Essentially, the resonant cavity here are 2 optical surfaces, essentially mirrors, coated reflectively. And as light enters this resonant cavity, it can constructively or destructively interfere. And the net result is that it basically operates as a wavelength filter. So we have only the wavelengths of interest to us that are eventually passed on to the L3 lens assembly to be focused onto the detector. So looking at the other charts there on the bottom there's the bandpass filter that I talked about. The vertical axis in this case is basically the transmission index going from 0 to 1. And the horizontal the horizontal axis rather is the wavelength, and you can sort of see the ability of the instrument to resolve the key absorption features of interest in the tozer and the top of atmosphere spectral radiance. So on the far right, there's another chart under the label of Fabry-Perot. So in a representative way, there's more of these, but there's like 3 colors here, and what this is representing is that these are basically in the case where the light is not normal incident to the Fabry-Perot, but comes in at some kind of incidence angle. And so when the incident angle is non-normal, it basically shifts the wavelength down. And so what this enables us to do with this with the spectrometer is that we're sweeping continuously across the tozer to get a sample of the continuum of wavelengths of relevance and to extract each of these spectral features within the bandpass. So sort of putting this in action, if in a hypothetical world we were to point this spectrometer down at a hypothetical featureless terrain of some kind. Obviously, there's no such thing, but presumably something like, say like a desert somewhere, or something that is relatively featureless, then the only variation in the signal on the Fabry-Perot would be the actual transmission features from sampling the spectrum. And so in this case, circular symmetry does hold. So ultimately what this manifests as basically rings on the imaging plane of the Fabry-Perot interferometer as we step through the absorption spectrum. So effectively what the instrument is doing is mapping the wavelength onto this onto the plane as a function of radius, and we have a corresponding proprietary instrument model that quantifies this dependence, and it's from this dependence that we ultimately extract both the surface albedo and the per pixel methane concentration. So let's look at what this looks like if we're to apply to a real observation. So the real Earth is, of course, not featureless, although, as I said, things like desert environments, are perhaps a close approximation. But they would probably look more something like this. So I've always thought that this looked a bit like somebody's eyeball or something. But what it actually is it's a river, and it's a dammed river, and then so the dark blotch there is actually the lake or the reservoir that's been created by a hydroelectric dam on the river. And this was actually something of interest to me, that before I joined GHGSat, I hadn't realized that hydroelectric dams are actually a significant source of methane emissions, and that's because as water comes through the sluices, decaying biomatter in the water that does produce the methane comes out of solution and ultimately into the atmosphere. So a typical observation sequence for us, as the satellite is passing overhead about 7.5 kilometers per second, the image sequence is roughly about 200 observations, where we also pan the instrument along the along track. So basically the target passes, and you can sort of see that on the animation, sort of the left animation, the grayscale animation there, where the features are sort of, if you were passing from the top to the bottom of this particular in this particular example. And you can also see the rings I talked about superimposed on this albedo image of the ground. So at the end of the day, of course, what we're really interested in is the methane concentration per pixel with respect to the ground. So in order to change it to a ground-based frame of reference, we need to do an image co-registration. And once that co-registration is applied, we're in that ground-based frame of reference. That's sort of the middle sort of animation there, where the ground features, the lake and the river are still, and the imaging plane, or the rings of the Fabry-Perot, if you will, are sweeping from are now the thing in relative motion. And so what's on the right here you see is the plot of the signal as a function of how far away it is from the center of the ring. So as I said earlier, effectively we're mapping the signal as a function of the radius. And this is the domain in which our instrument model operates. And again, this is shown on the right here, where we have the different color coding. The different color coding of the data points is meant to represent which particular frame that a given data point came from. And as we would then compare these data points to our model and derive a best fit. And the parameters of this fit would include things like, well, the most key thing, of course, the methane concentration in each pixel, and the background surface reflectance. That was a very, very quick overview. What I would encourage is, if you want more details of this methodology, there is a paper by my colleague Dylan Jervis that was published in Atmospheric Measurement Techniques. And if you scan that QR code there, that will take you directly to the paper. All right, so what's the result of this particular procedure? So again, the two most important retrieval quantities that we're interested in is the background albedo and the enhancement of methane concentration per pixel above the background rather, in the 12 by 12 kilometer field of view. Actually, maybe I'll back that up a bit. That you see that sort of potato-like sort of elongated field of view there. So the nominal field of view is 12 kilometers in the cross track of the satellite, but we do have the capability to leave the sensor on for a little bit longer in the along track. So typically that could be between 12 to 15 or greater kilometers, and hence that elongated field of view that you see in the grayscale albedo on the left. So as part of our procedure, we need to estimate the average background methane concentration, and then we subtract that out, and that's how we get the enhancement, the local enhancement, the point source above the background. And it's a way of also filtering out things like artifacts as well. So the image on the right shows column density. This is in units in moles per meter squared. And in this particular example anyway, which was actually based on a controlled release we did from a site in southwestern Alberta, the mean background methane density was about 0.64 moles per meter squared. You see the color scale here going from approximately 0.1 to a negative 0.1 deviation from that mean in moles per meter squared. So about plus or minus 15% of the background value in this particular scene. So what you see on the right from the raw retrieval, it looks like this sort of very colorful, sort of specular almost type of imagery. And then I don't know if my mouse is making any sort of a pointer at all, but there is a bit of a reddish area here that looks like some kind of a local enhancement. So if we were to zoom in on that particular blob, again, this was from a controlled release experiment. In that case, we were coordinating this observation with a ground team that was releasing the methane at some known rate at the time that our satellite was passing overhead. And so the ground truth was 360 kilograms per hour, and the retrieved estimate from the satellite was 388 kilograms per hour. And this is taking into account the error bounds of these measurements. They are well within the expected values. In this particular case, the peak plume enhancement was about just about 8.59 times the background level that I talked about earlier. So this is something that gives us confidence that this is a real methane enhancement and not some kind of an artifact. So as instrumentation people, you're obviously very familiar with and recognizing the importance of calibration and validation. So in the earlier slide, I mentioned sort of this two branches of satellite observations, these wide area flux imagers, flux mappers versus point source imagers like ours. So for the global flux imagers, the quantity of interest was the absolute concentration levels, the absolute column density measurement. So there have been a number of different ways to calibrate and validate these. One of these is a network called TCON, and help me here. I think it's something like Total Carbon Column Observation Network, I believe. So this is a number of sites around the world that are basically sun pointing and look at the absolute column concentration, and the satellite observations would be compared to these TCON observations, the TCON measurements on the ground. But for the point source imagers like GHGSat, what we're really interested in is how good we are being able to distinguish a methane plume, a methane event above the local background level, and to differentiate that from any artifacts or errors. So this really requires a good assessment of the overall background level. And so so maybe I'll just flip to the next slide here about how we determine our column precision. So the procedure for doing this, for determining the column density precision, is empirical. We basically take a relatively small retrieval field, a relatively small region of interest, say on the order of about 500 by 500 meters, and we would pick an area in the field where there is not supposed to be either a plume or any sort of artifact type event. And really what we're quantifying here is the standard deviation within this 500 by 500 meters. And we sort of do this over and over again, not only within one scene, but across literally tens of thousands of observations across all seasons and across all terrain types. And empirically, we just bring that all together. And what we have here is literally over these tens of thousands of observations, we plot them. We plot them as a histogram shown here on the top right. And the histogram is basically showing the frequency of any given standard deviation. And so, looking at that, we see that empirically, we've determined the median column precision density is 2.1% of background. Actually, I'm going to go back. Sorry, I thought I had a paper reference to this, but I think it's a little bit later on. Yeah. So the two other quantities of interest that need validation are detection threshold and the emission rate. And the gold standard for doing this is the single blind controlled release test, where I think I mentioned this earlier, that there is some known ground truth, some metered ground truth on the ground. Satellite passes overhead. We do the retrieval. We determine the emission rate and then compare notes after the fact. So we've done this internally. In this case, this is a site that we use frequently. It's called the CAMI site in southwestern Alberta, in partnership with a local college over there as well. And we've done these controlled release tests with academia and other research groups as well. Most notably, a big effort by Adam Brandt's group at Stanford, which I'll talk about a little later. So In terms of quantifying our detection limit, this is probably one of the two key parameters of interest to us. The other being, of course, the emission rate itself. So basically, how well are we able to detect a plume at a given source rate, and particularly important, the function of the local wind speed. So what you see plotted there are a number of observations. So the positive detections are given in the blue diamonds, and in the cases where we have a null detection is in the sort of the green sort of X's there. The ones that the blue diamonds that are circled in black, these are independent controlled blind sort single blind controlled release tests that we've done with people like Stanford and others. And maybe important to realize as well is, the green X doesn't necessarily mean that there was no emission there. It's just that it wasn't picked up by the satellite. So it was a one way or the other. It was below our detection threshold. So we plot these all out, and intuitively this makes sense that the higher the source rate and the lower the local wind speed, the greater the number of detections we have. So basically, at this point, it becomes a bit of a statistical exercise. We fit this binary detection data and put it in a regression model. And we also took from the literature a probabilistic detection model, which we rolled into this. And that's actually sort of the third dimension in this chart here. So going from black sort of fading out to a whitish is probability of detection going from 0 to 100%. So where this all comes out, so at the end of the day, based on the data that we've measured since, also the real data from about 2021, when our first commercial satellites became operational, we have quantified a detection threshold of 100 kilograms per hour at 50% probability of detection in a 3 meter per second local wind speed. At 90% probability of detection, the threshold is about 156 kilograms per hour. So I've got a QR code on the top right there. If you were to grab that, that will take you to an internal white paper that our internal science team has produced, which documents this whole quantification of the detection limit and the quantification of the background error to a far more detailed extent than what I have here. So the last valuable quantity that comes out of the controlled releases is to ensure the accuracy of our emission rate quantification. So the emission rate is derived through a methodology known as integrated mass enhancement, which I don't have a slide for that, but if you scan the QR code here to this particular paper, it takes you through that particular methodology. So controlled releases, we've been doing this for a very long time. The image on the left here is a controlled release we actually did with an oil and gas operator. This was Total Energy of France. In this case, the satellite measured was 250 kilograms per hour plus or minus 140, and the ground truth was 234 kilograms per hour. So we were under 10% here. And the correlation chart on the right is taken from actually it was a science paper, I believe, from Nature rather. Sorry. So this was Adam Brandt's group, Evan Sherman. They did a number of controlled releases, not just with our satellites, but other satellite systems and some UAVs and aircraft as well. And in this case, we were plus or minus 20% of the ground truth value for all the cases that were studied. And the other noteworthy I'll start concluding here by emphasizing that the point source imagers that GHGSat, what we do, is entirely complementary to these big wide field area flux mappers. So I talked about the TROPOMI instrument earlier, this thing that looks at 2,500 kilometer swaths, but at 5.5 by 7 kilometer pixels and has several tons of detection threshold. So what we do with them, we've had a collaboration with SRON. This is the Dutch Space Science Institute since 2019, where they look at the observations for TROPOMI and they basically tip and cue us. So their satellite, the TROPOMI instrument, goes over some region of the world, in a wide swath, and say, hey, there's an elevated methane hotspot here, of several kilometers. Can you GHGSat have a look and sort of look, sort of almost like a kind of like a methane telescope to zoom in on that and use that low detection threshold, high spatial resolution to pinpoint exactly where the source of that emission is coming from. And again, this is something that we've done with great success with the SRON and TROPOMI crew over a number of years. And if you want more details of that, I have the QR code for the paper from GRL. I promised in the abstract to talk a little bit about the relevance of all this to disaster management. So very recently, I'm sure we're all familiar with the events in Los Angeles just at the start of the year. So we were actually contacted through something called the NASA Disaster Response Coordination System to see if our satellites could detect whether there were any methane leaks, natural gas leaks coming from basically residential gas distribution systems that may have been compromised as a result of these terrible fires. So over about the course of a week, we made over 15 observations of this area. I'm not showing here a plume because the good news is we actually didn't see anything, or at least nothing that was above the 100 kilogram per hour detection threshold of our satellites. The image on the left was from about 2 years ago now. There was a terrible earthquake in Turkey in February of 2023. In that case, we were contacted by the authorities there. This was their national oil and gas company, and they needed to know whether any of their pipeline infrastructure had been damaged and was leaking as a result of the earthquake. So we had to look there. And again, the good news is actually I don't have a plume to show you because we didn't detect anything that was above the 100 kilogram per hour threshold of our satellites. In the case of the Turkey earthquake, we do know that there were other leaks that were much smaller in magnitude. They flew around some UAVs and helicopters, but the good news there was that there were none of these sort of mega emitter or super emitter type of events that were a result of the damage from the earthquake. So maybe as a one last thing, where we did see a very big plume a year before in September 2022, there was a suspected sabotage of the Nord Stream pipeline. And we actually did see a number of plumes in this case, and these were some of the largest plumes we've ever observed rather, either on land, on water. At one time, it peaked out at I think the middle image there was 79 tons per hour. I think there was something like this wouldn't be the equivalent of like 2 million pounds of coal being burned every hour. This was an outrageous amount. This is actually documented in a new paper in Nature. If you're interested in this, you can follow scan the QR code there. Maybe just as one quick thing, I'll mention that there's challenges associated with observing over water versus land. So as you may recall, that our instrument is passive, operates in the SWIR, in the shortwave infrared. Water tends to absorb in the shortwave infrared, so there's different operational techniques we need to employ to observe over water. It's something called glint mode, and basically we try to optimize our viewing angle with the solar zenith angle, try to maximize the sun glint behind the plume in order to increase the signal to noise, and to suss out a retrieval out of that particular background. If there's interest, a few links here to some other cases where our technology has proven useful in emergency response and disaster situations. I'll conclude now. I'll really conclude now with just a note that I do realize that I'm talking to a largely instrumentation group, but for maybe some of the more pure research scientists, our data is actually available for free to the scientific community through NASA, through the Commercial Smallsat Data Acquisition Program. For the European colleagues, there's an analogous program called the Third Party Missions Program that makes our data available for free to any researcher in the world. And if you're in the United Kingdom, there's another mechanism there called the Applications Catapult, which is another way for applications developers and scientific researchers to use our data for free. If you're interested in NASA data, you go to the Earth Data Portal of NASA, create a profile. It'll take you to something called the SDX, the Small Sat or Satellite Data Explorer platform, where you can download data that either we've already delivered to NASA or request new taskings for things that they may not already have in their holdings. So I'll leave it there. And one last QR code, which takes you to our page that has a list of our scientific publications and white papers that provide in a lot more detail than what I've tried to convey in this short presentation. So with that, I thank you so much for this opportunity to speak this afternoon, and I'm happy to take questions.
Hi, let me try. Well, no, let me go. Yeah. Questions. Thanks so much, Eric. Well, actually, hopefully you can both hear me and hear him. Excellent presentation and really appreciated all the technical detail. I think it was really informative for this audience to see the process, and I'm very impressed with the scientific aspect of what your company shares with the public in terms of how you process the data and how you validated it and so on. Not a lot of organizations go through that level and publish in scientific journals, so that's great to see. So this time we're open to any questions here. We have a couple dozen people in the room and
That's great.
online. So any questions? I don't see any hands in the room. I don't see any in the chat. One question I had, you mentioned the data through the NASA portal, and I was just curious, what level of processing is available? Is it only like the final product? And the motivation for the question is, are there data there that other people could then apply their own algorithms or use as an exercise to understand how to do that?
Yeah, that's a great question. So the data that's available, if you'll forgive me for using I guess it's the NASA EOS disk terminology. So it's level 2 and level 4 data. So the level 2 data is you would get that albedo image that I showed and the per pixel georeferenced methane concentration as a geotiff file with an associated error layer to that, so it flags bad pixels. And then there's a level 4 data, which is the emission rate estimate with the error bars, and so that's a CSV file. We are not able to provide the level 0 and level 1 data. Basically, we don't provide the raw counts because as I went through earlier in the slides, it's kind of the Fabry-Perot is a bit of a non-standard instrument configuration. Like it's not like a grading spectrometer or something that is readily published in the literature, and so the data itself would not have meaning unless the particular user also had the instrument model that I alluded to that we do the fit to. And the challenge there is that there are commercially sensitive aspects to the instrument model. So it's to make a long story. So it would be the georeference geotiff, the level 2 data is the lowest level data that's currently available through NASA CSDA.
Okay, and I think you said that's like an albedo product, a reflectance factor.
So there's the surface reflectance and the per pixel methane concentration. So it's actually two files. I was mistaken.
Okay, got it. Perfect. I should have mentioned this at the beginning, but Eric was planning to be here, but unfortunately was not able to travel down, and so that's why we had to pivot to this remote presentation. But I think you did a great job of presenting and really appreciated the level of detail. As I said, is very clear. And I know that you chatted with a few other folks earlier in the day. We certainly hope at some point in the future you can make a visit for more discussions. One last call for any.
Certainly hope so as well. I'm physically not that far away, just across the lake as the crow flies. So here are my coordinates. I'm also on LinkedIn and well, professionally on day job GHGSat on LinkedIn. For those who may have a morbid curiosity about my science fiction writing, my social media handle is Aerospace Writer, so you can find me on most of the social platforms as Aerospace Writer.
Great, perfect. Okay, well, thanks again, Eric, and hopefully I'll see you in April, or if not, at a
At
future
AC,
time.
yeah, I hope so.
Perfect. Thank you.
Thank you, everyone. Have a great day. Thanks for this opportunity.
Okay. Thanks, everyone. Thanks, Eduardo. Of course, got